The RSA Algorithm Examples. So Alice wants to send Bob her message, and she chooses two primes, P and Q, and calculates n, which is P times Q, and phi of n, which as we saw in the previous video is just going to be P minus 1 times Q minus 1. And she chooses an exponent E, the encryption exponent, so that the greatest common divisor of E and phi of n is equal to 1. And she calculates the decryption key D, where D is the inverse of E mod phi of n. That's why it had to be relatively prime to phi of n, so it has an inverse. She publicizes n and E and keeps D, P, and Q secret. Now anybody that could factor n could calculate D as well, but the idea is P and Q are going to be such huge primes that it's very difficult to factor n into the prime factors P and Q, and without having those prime factors you can't calculate D. Okay, so Bob wants to send a message to Alice, then he's going to look up n and E, which she's made public. He doesn't have to know P and Q to send a message. You only need P and Q to decrypt the message. So Bob writes his message M, and I'll show you how to do that in a few moments, and computes the ciphertext, which is m to the e power mod n, and sends that ciphertext message to Alice. Alice receives C from Bob, and she computes the message back, which is a ciphertext to the d power mod n. Okay, so let's look at a small example. A message was encrypted using the RSA algorithm with n equals 323 and e is 173. We want to find D. So the first thing we have to do is calculate phi of n, and in order to do that we have to figure out P and Q, the two primes that multiply together to get n. So if you factor 173, so if you factor 323, it turns out to be 17 times 19. So phi of n is going to be 16 times 18, which is 288. So we can pick e to be any exponent in this example as long as it's relatively prime to 288. And in fact, 173 is. Okay, so to calculate D, D is the inverse of E mod 288. So we've done this before. 1 is congruent to 289. We see if 173 divides into that. It doesn't. We get 577 and 865, and 865 turns out to be 5 times 173, so D is 5. Okay, so let's take a look at how encryption and decryption works. Here we've got n is 323 and e is 173. We just calculated the D value of 5. And we've got a message, 139. So in RSA algorithm, the encrypted messages are numbers. So we want to take 139, raise it to the 5th power, mod 323. Even 139 to the 5th power is going to be a pretty huge number, but we want to reduce that mod 323. So let's get our calculators out. So it's going to be 139 to the 5th divided by 323. Then we have to subtract off the whole number part there, which you probably have to write down. It's 160646578. Then we're going to take that value, which is the decimal part, and multiply back by 323, and we get 5. So we got 139 to the 5th reduces to 5 mod 323. Now how do we figure out the secret letter? Well, in the RSA algorithm is the only one that we actually start counting at 1 alphabet. So you gotta keep that in mind. So the secret letter was the letter E. So now how does it work when we encrypt a message? So my message is hi. I'm going to look up the corresponding codes. Now what we're going to do is and notice we have a leading 0 here. So we got 0809. Putting that together to get the number 809. Okay, the leading 0 drops off from the number. Then we're going to take 809, raise it to the 7th power, mod 3599. So we got 809 to the 7th. And now that number is so huge, it's going to be difficult for us to subtract off the whole number part, since it's given to us in scientific notation. So we're going to use our friend Mathematica for this problem, and PowerMod. So the command you would do is PowerMod. We use this for inverses, but we want to take 809, raise it to the 7th power, mod 3599, and if you type that into Mathematica, you'll get 1784. So that's the ciphertext. That's the message that goes. Okay, so to see how this decrypts, we didn't need to find the inverse of the exponent, not mod 3599, mod Euler phi of 3599. So D turns out to be 2983. We're going to take the ciphertext 1784, raise it to the 2983, mod 3599. So we're going to again use our friend Mathematica and the PowerMod command. So that would be PowerMod of 1784, comma 2983, comma 3599. And guess what? We get 809. Now to figure out what the message is, basically you start from the ones and separate into blocks of 2. So we lost a leading 0 here, and the 8th letter is H, and the 9th letter is I. So hi is our message. Okay, example 4. Alice chooses P and Q as given, calculates N, that's going to be the public key, and she chooses E is 233. Bob wants to set up a meeting with Alice, and he decides they should meet at the car. So what Bob does is look up the codes, 03, 01, 18. So the message becomes 030118, and we take that message to the 233rd power, mod N, where N is this nice big number up here. That we're definitely going to need our PowerMod for. And that gives us our ciphertext. So that is the message that is sent. So Alice receives this message C and uses her secret key D to decrypt the message. And we get back 30118, which again is the message car. I hope that helps, and you have a wonderful day.